This video is part 2 of a series about using simple continued fractions to solve linear Diophantine equations. We'll go over the process step by step for doing just that, solving the equations using simple continued fractions. Let's get started. As discussed in part 1, the form of the equation we will use is ax plus or minus by equals plus or minus c. A, b, and c are positive integers, a and b are coprime, which means they don't have a common factor greater than 1. These conditions assure us that there are integer combinations of x and y that satisfy the equation. In fact, there's an infinite number of them. If you are interested in more about the equation itself, please see part 1 of this series. The process we'll show here is broken into 4 steps. The first step is to expand a over b into a simple continued fraction, a0, a1, a2, and it might continue on for a while, but it will end. We'll label the last two terms a sub n minus 1 and a sub n. If you don't know how to expand a rational number into a simple continued fraction, please see this other video. Here's step 2. If negative 1 raised to the n plus 1 power does not equal the sign of the right-hand side of the equation, then convert the simple continued fraction to its longer representation. We'll discuss what this means on the blackboard a little. N is a subscript of the last term in the simple continued fraction, this n right here. And the sign of the right-hand side of the equation is whatever is before c, plus or minus 1. We'll just touch on what it means to convert a simple continued fraction to its longer representation. Let's say that when you expand a over b, the result is 4, 1, 2, 3. This is what we can call the shorter representation. When you expand a rational number, the result is the shorter representation. It can be converted to the longer representation, which would be 4, 1, 2, 2, 1. The last term, the 3, was replaced by 2, which is 1 less than 3, and there's a 1 appended to the end. That additional term makes it longer by 1 term, so we can call it the longer representation. The process for converting to the longer representation, if you need to do it in step 2, is subtract 1 from a sub n and append 1 at the end. You don't always need to do this though, only if minus 1 raised to the n plus 1 power is not equal to the sign of the right-hand side. There's a separate video about the shorter and longer representations if you'd like more information. Step 3. Calculate the convergence of the simple continued fraction, either the convergence for the original one, the shorter representation, or if you had to convert it in step 2, the convergence for the longer representation. If you aren't sure how to calculate the convergence, there's a separate video about that too. The last step is to calculate values of x and y. There are two different sets of expressions to use, depending on whether the equation you're solving is of the form ax plus by equals plus or minus c, or if it's ax minus by equals plus or minus c. If it's ax plus by equals plus or minus c, then the expression for x is x equals c times q sub n minus 1 minus b times t. B and c are two of the positive integers from the original equation. Q sub n minus 1 is the denominator of the second to last convergent, and t represents a set of all integers, including 0, positive, and negative. We'll write out the meaning of t soon, but first let's see the other expressions. Y equals negative c times p sub n minus 1 plus a times t. A and c are from the original equation. P sub n minus 1 is the numerator of the second to last convergent, and t represents a set of integers again. If the equation you're solving has the form ax minus by equals plus or minus c, in this case x equals c times q sub n minus 1 plus b times t, and y equals c times p sub n minus 1 plus a times t. Just like before, a, b, and c are from the original equation. P sub n minus 1 and q sub n minus 1 are the numerator and the denominator of the second to last convergent, and t equals the set of all integers, including 0, and the positive and negative values. That's it for the process. In the next parts, we'll use it to work examples. In this video, we gave a step-by-step process for using simple continued fractions to solve linear Diophantine equations. That's all for now.